All right. So you know that at point D, the equivalence point, all of the acid is gone. So all of that acid has been turned into the conjugate base. So whatever the concentration of that acid is, that is now conjugate base because the NaOH has basically taken care of that. Well, that's the thing. You use the Ka. That's why you're using a Rice table versus a BCA table, right? So then you start off with the concentration of the. This is the important part. You need to make sure you divide by the new volume because now you've added the acid and the base together. So you take the moles of the acid that you started with, you divide that by the new volume in liters, and that starts your molarity of the conjugate base, right? And then you minus X, and the acid and the well, the H2O doesn't matter, but you minus the X, and then that adds X of both things to the other side. I will tell you that that last one is going to be your worst one. Yep. In reality, it may be one that you want to drop. Well, usually we get rid of outliers, right? How far? You said it's often by a magnitude, right? So if you're looking at the other things, right? Then yeah, I would probably average it. Don't put that in the average, and then you may get a better thing. In reality, how many of you found that the molar mass was actually a better predictive measure? Yeah, right. Yeah, so that's kind of cool. That's a backup, or something that helps you predict it as well. So what did you if you had A, who was our Aer? Was that you, Lilia? You what did you get for
I got that it was like the potassium phosphate.
Yep. And if you took a look, it was actually PP written on the bottom. Yep. And then you had C, and that was KHP. Is that what you identified it as? And then somebody had a trick one. Who was that? Yeah, it didn't work out, right? Are you okay with what were you okay with using somebody else's data? Okay, cool. Does that answer your question, Dylan? These other questions, if you emailed me, I'm not going to read these until probably 10th period, and then I just may walk out here without answering them. So if I didn't answer yours, would you please make sure? Once again, I don't know. Figure out initial. Okay, we just went over that. Yep, the conjugate base. Yeah, by all means. I mean, in reality, I mean, like, yeah, I don't care about stuff like that, right? I'm not going to grade them probably until over spring break or something, right? Yeah.
Is there a time that we can come like get help?
What is today? Wednesday? Tuesday? Support hours are Wednesday and Thursday. But I mean, after this Zoom or whatnot. But I think I answered your question. Basically, here, let me show you with the data table. The visualizer. Yeah, those of you that I think Diego, you are signed up for to be here. So I just want to let you know that some teachers may be really weird about this. I don't care, but they do have the ability to count you absent. I think actually I have to count you absent. And some teachers, if they block off the Zoom call, they may not let you have access in because you are signed up for in person.
Oh God.
I know it sounds crazy. I just want to let you know I have to mark you absent, I think. So if
Yeah,
person, you may want to
it's fine.
you get that change. That's school policy on that. I don't know if it's funding or what. But I'm not gonna, I mean, I don't even have time to let people into the Zoom more or less. block people from entering the Zoom. Don't Zoom bomb me though. All right, so take a look here. I think Peyton, this will help you out. So if we take a look, you can't see it because I'm not sharing it. Now I'm sharing it. All right. So if we take a look here, we know that 0.00952 was the number of moles for that acid. We know that since it's a monoprotic acid, it took 0.00952 moles of the base as well, because OH pairs with the hydrogen that comes off and making water. So then if we take that and we divide it by the total volume of the acid, which that was why it was important that we use 100 milliliters, and the total volume of the base used to titrate, these may not be your numbers, right? Then we get 121.25. We change that to liters and we divide the 0.00952 by the number of liters, and that gets us the molarity. That's what we put in that ice table. The other trick here is we've got to use for this the KB, because that that conjugate base is going to form hydroxide ion. All right. That means we're solving for the KB. Is that why? Let me check. I wonder. I'm sorry. I can't hear you. At equivalent. Right here. So basically we have X because we know the hydroxide ion concentration from the pH right here. So we find the hydrogen ion concentration, then we use negative log of this, and then we take 1 times 10, or we can take 14 minus this, right? And that gives us the OH.
Okay, so to find the concentration of the A negative, you take the same number of moles that you had in all the others, and then you divide it by what you have in the volumes on the right.
Volume, you got it. The addition of the summation of the volume. Yep.
Okay. Is the 100 the same for everybody? Because that was in the procedure.
It should be. I didn't closely watch everybody's procedure, but I think that everybody used 100, right? Yeah.
Okay, thank you.
You're welcome. Yeah, so then we get that for the KB, and then we need to take 1 times 10 to the negative 14 divided by that, and that gives us the KA. And you can see I was off by an order of magnitude as well, right? I'm sorry. Yeah, I would, because you can see it is way far off. I think that the purpose of you getting point B is so that you can sit there and say, oh wait, I can get the numbers for this. Problems with it, one is probably we're using a pH meter. They're not the best instrument. They're the best that we have, right? But the ones that we actually, if you remember last semester we used those ones and they were very shaky. The ones this semester, if you mix it well, they do give you a set number. Other questions? All right, I'm gonna pass out what's called the buffer lab. We're gonna talk about buffers a little bit. And basically that's gonna take us into spring break. So if you hated this lab, oh wait, you're gonna really hate the next one. We played this game. Like for 12 years now. But so we have a limit. But if I take more than the top, they have been down. We get that. None of you know that. I would do that to them probably. Yeah. But I'll probably still know how to do it. They'll be like, what happened? You know, well, the rule is that making more than 3. Like, I'm gonna leave that there. If that's something that you want, go for it. That's good. I think that's probably the safest way we can do it. But it's funny, what we would do is basically we'd take pictures and send like your papers drawn about the room. Yeah. But the reason for that was like sometimes at different points in your career, you're like, oh no, I need to print a copy of this right now. And then you end up walking in there and somebody's sitting there printing out 40 things and you're like, really? Really? So that's what caused the throw your papers on the ground game. Yeah, it was fun. There was like a brand new teacher about 5 years ago, Justin. He only lasted 2 years before he moved up to Westfield. Couldn't hack North Central. Maybe. But I remember the first time he's like, really guys, is this what we do? Like this innocent new teacher face. Like, yeah. Like, dude, it's cutthroat. No one is safe. Put your papers to the ground. All right. All right. Hopefully you were able to find this at home. So let's take a look. The first thing with acids is it's important to understand that they resist changes if an acid, I'm sorry. The first thing with buffers is it's important to remember that they resist changes if an acid is added or a base. They resist any of those changes. Trying to think, you may have been exposed to buffers. There actually is a medicine called Bufferin. I don't know if that's how it's spelled, but that's how I'm going to spell it for this lesson. If we take a look, let's take a look at see if I can find see if they still make Bufferin. What's that? Yes, it is just an aspirin brand. So like Tylenol and stuff like that, you could use Bufferin. Let's see what the images look like. So this is Bufferin. Now take a look here. It is buffered aspirin. So aspirin is actually acetylsalicylic acid. And it was originally found to be in tree bark. And ancient civilizations would basically, if they were in pain, they would sit there and nibble on tree bark, and they were able to get some of this acetylsalicylic acid out. Later on, we were able to chemically manufacture it. The problem with it is that it is an acid. So what that would do is that would introduce a more acidic environment into your stomach, and this was feared to have caused what we call ulcers, which are damages in your stomach lining due to the protective, basically, like phlegm layer, like the nasty, stuff that protects mucus. Yeah, the mucus that protects the lining of your stomach, breaking down and then actually infecting the lining of your stomach. So buffered aspirin or Bufferin was used instead. But what that did was that allowed the aspirin to not change the pH or whatnot of your stomach. So that is why we called it Bufferin. So I'm trying to think of other examples that you might have with a buffer. A lot of times they'll say stuff like pH balance for shampoo and conditioner and stuff like that. Soaps tend to be more basic, but what they can do is they can put a buffer in there or something like that to basically maintain that pH balance or whatnot. Other than that, you're in contact with it every day. As it says here, your blood needs to maintain a pH of between 7.34 or 35 and 7.45. It can't vary that much. The way your blood does this is by using carbonate and carbonic acid. Basically, carbon dioxide, CO2. If your blood pH gets too high, you start breathing out more and breathing in more. And it's the same thing with what's the hyperventilating, that whole CO2 thing. This is part of that. Your body has a way of protecting itself from changes that it undergoes. So that's what this buffered system does. So we take a look. Here is our Henderson-Hasselbalch equation. Here is kind of the cool thing. If we take a look, if the acid and the conjugate base are of equal concentration, what is this ratio going to be equal to? Yeah, it'll be equal to 1, and then the log of 1 is 0, right? Everybody get that? If this is equal to this, that's going to be x over x, which is 1. And then the log of 1 is 0. So what that means is that the pH will equal the pKa. In order for a buffer to have maximum buffering capacity, the ratio of acid to conjugate base should be close to 1. And the pH of that solution will then be close to the pKa of the weak acid. So basically, you're going to get a pH, and you're going to have to make a buffer. You want the pKa of the weak acid to be as close to the pH that you're given as possible. That will make it a stronger buffer. The reason for that is it's a 1-to-1 ratio. You can make a lot of different pHs with buffering systems by putting a lot of one of these in or a lot of this in. The problem is it won't be as equivalent as a buffer because there'll be one weakness, one way, either adding an acid or a base to it will be its weak part, right? So keep that in mind. A buffer is broken when the amount of acid or base in the solution completely neutralizes the acid is completely neutralized by a strong acid or strong base. So again, that equivalence point is going to be a point of interest for you. We will titrate these buffers on Friday, hopefully. But that's our plan. So here's the pre-lab. I'll give you some time, hopefully today, to work through this, and then I'll give pHs to these guys, and they can think about how to make their buffer with your help at home or with the help of each other. Acid-base pair combinations. So here are the 4 ways we are going to make buffers. Sodium bicarbonate and sodium carbonate, acetic acid and sodium acetate. Now, I'm not going to give you guys glacial acetic acid. I'm going to give you guys 1 molar. We are using potassium phosphate and potassium phosphate dibasic. So let's cross out the sodium there so that whenever we're calculating our molar masses for this, we don't get that confused. We want to get the molar mass for these guys. I am using concentrated ammonia. Have you guys used pipettes before? Okay. What's that? Like these? Okay. So if you've used one of those, then I would be more comfortable for you using that that concentrated ammonia, because basically you want to get it over there under the fume hood. We're using 1 molar acetic acid because we can use that outside of the fume hood. But if you have one that has a high pH, you need to make that buffer, then it's best if you do that. I didn't want to dilute it because it doesn't last very well. Concentrated ammonia is 13.4 molar. So the cool thing is, if you are doing this one or this one, you need to make sure that you use M1V1 equals M2V2. If you are using this one or this one, all of your stuff will be based off of molar mass and grams, because you'll be measuring it out with solid. Yeah. We will be making 250 milliliters of this. So your first task will be to make a buffered solution of defined pH. I will check that using the pH meter. You will call me over and say, hey, check a look at this. And then I will initial whatever this last page is. The verification table. That's the first task, is to make it. Easy enough. The second task is then to titrate it. Before you titrate it, you should find out how much NaOH or HCl, whichever you choose. Obviously, if you have a pH that's higher, you'll probably choose the HCl to break it. If you have a pH that's lower, you'll probably choose the NaOH to break it. But you will find out how much that should be. Well, what does it break at? It breaks whenever you either add enough acid to take care of the base, or add enough base to take care of the acid in the bucket, right? So your choice on that entirely. That's when the moles are equal to the moles, whichever way you decide to go. You'll calculate how much that is. Now, the other thing with this is also we need to check, since we are titrating and we're not doing acetic acid and sodium hydroxide like we did before, you will need to calculate the pH at which you will break it. That pH, you will then need to check on, let's see if I got it, on this indicator sheet. Let me share this with you. And this indicator sheet will tell you which indicator you should use. So if we take a look, here are the indicators. We use phenolphthalein because the point at which it switched was between 8 and 10. And acetic acid, that would break and ended up at like 8.6. If instead you've got a breaking point, let's say that 8.2 to 9.6, you would use thymol blue. 6.8 to 7.6, you would use bromothymol blue. What you'd be looking for instead of that turning pink, you would look at it as yellow until it turned blue. The other thing is, let's say it was closer to 6.8 and you were adding acid to it to titrate because yours was high, then it would go from blue to yellow. You can go either way on this, right? So not only do you need to make the buffer and titrate the buffer, but you need to check before you do your titration where the breaking point will be and which indicator you want to use for that. What do we think? Put you into groups and talk, or do we need to discuss this making the buffer a little bit more? Discuss? You're not comfortable? All right, so let's imagine one of the key things is we can't use all the chemicals in the laboratory. So I don't want you to use more than 5 grams of any chemical. We're limiting you to that. So we know that we are making 0.250 liters of a buffered solution. Right? Let's say that we want a pH of 11. Out of these things, what do you think we will use? This has a Ka of 4.8 times 10 to the negative 11, right? We want something that has the pKa close to 11. That will be the best buffer solution. So if we take the negative log of 4.8 times 10 to the negative 11, would that work? We get 10.3. Would that work? Yeah. So that would be a candidate. Let's take a look at this one down here, concentrated ammonia and ammonium chloride. So we have the Kb here. So 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. We get that. We take the negative log of the Ka there. Oh. And we get 9.25 or 9.26. Will that work? Probably not as good, right? The top one would be better for this. Would be better. All right, so we have sodium bicarbonate and we have sodium carbonate. So sodium bicarbonate in a HCO3. In reality, this will become a spectator ion. So what can this do? Take an H, donate an H, or take an H, right? We could add an H on here and get H2CO3, or we could donate an H and get CO3 negative. If we do make H2CO3, what does that break down into decomposition-wise? H2O and CO2, right? That's how your body regulates. It takes H2O, CO3 whenever you have a buildup of acid in your muscle tissue or your blood. It can take that H2CO3, break it down into water and carbon dioxide, and then that means you breathe out more what? Carbon dioxide, and we get rid of that acidity. What's the acid that builds up in your blood, sports girl? Lactic acid, right? If you're a runner or something like that, don't you run in the sports ball, in the softball? Right? You build up that. What do you end up doing whenever you run cross country? What do you end up doing more of? Breathing, right? One is to get oxygen, the other is to expel that CO2. Keep that blood pH up in that case, right? All right, so we could do either. But let's take a look at what else we're dealing with. Sodium carbonate. So that is Na2CO3. Again, what do we know about Na? It's a spectator almost always, right? It's always soluble. So that would be -2. What can this one do? Accept. So if it accepts H plus, we are going to get HCO3 1 negative. And as we know, this one right here can do what? Can do both. But if we're not getting rid of it, breaking it down into carbon dioxide and water, because that's going to take the buffer out of the solution, what is it going to do? It's going to be able to give that up and form CO3 2 negative. So there's our buffering system, right? So this is our HA. And this is our A minus. We look at the Henderson-Hasselbalch equation. pKa plus this will equal pH. Well, what is the pH? 11. What is the pKa? Yeah, right. It was real close to it. 10 something. Uh, 10.3. All right, I'm just gonna go with you guys because I don't want to waste time. 10.3. Not that I don't keep you, but if this is wrong, I just want you to realize that I didn't have time to recheck it. And then we have this. Thank you. Monk is doing what he does best, and that's correcting me. We need the log of that in there. So mathematically, help me out here. We subtract 10.3 from both sides, right? So 11 minus these guys is 10.3. We get 0.7 equals the log of A minus over HA. What do we do here? 10 to the power of it, right? 10 to the power of both sides. So with this, I think you actually need to use the anti-log, which some people don't like that word. And we get 5. Uh, 5.01. So that means that we need 5.01, the concentration of A minus, to the concentration of HA. Right? So for a 1 molar solution of this, we would need the top to be 5 molar. Yes, yes? Well, the top is the sodium carbonate, 22.99 plus 12 times 2 plus 12.01 plus 16 times 3 is 105.99. That means that if I had a 5 molar solution, 0.25 liters, every 1 liter would be 5 moles. That would be 0.25 times 5 times 105.99. That would require me to use 132.5 grams of that sodium carbonate. Well, we said we didn't want to do that. We wanted to use closer to what? 5 grams. So that means that if I take 5 grams of the sodium bicarbonate, every 105.99 grams is 1 mole. 5 divided by 105.99. That will give me 0.047, right? What's that close to? 0.0 what? 5. I would be acceptable to go ahead and change this instead of 5 to 0.05 moles. What would that mean that this would have to be? 0.01, right? So if I used 5 grams, that would be close to, let's go ahead and do this. This is 5.0, and I think that this is how you guys would probably think about this. Instead of that, I want 0.050 moles, and that makes this X, right? What do they call these things? You guys are much better at this than me. Ratios, proportions, right? I think they taught you guys this better than they used to teach it to us. It's part of that whole new math program, right? So if we take a look here, what do I need to do? I need to take 0.050 and divide it by 5.01, and then that will tell me exactly what we've talked about theoretically in our minds. That means we're going with a 0.05 for the top and a 0.01 for the bottom, right? So that means we'll have a 0.05 to 0.01 ratio. Well, that is molarity. So with that now, can you make a 0.250 liter solution of, let's see, let's do it this way. A 0.250 liter solution containing 0.05 moles of the acid, I'm sorry, the conjugate base, and 0.01 moles per liter of the acid. Molarity. You could do moles too, but we are using if you do moles with this, you would still end up making the solution, but I think it might be weaker. Well, I mean, you would just do this, 0.25 liters. Every 1 liter is 0.05 moles. So every 1 mole of this solution, and I'm just going to do the top one here, is 105.99, hopefully, right? And that would tell you how many grams you would put into that. And then you would do the same thing for this bottom one, only using the NaHCO3. And that would tell you how many grams of that to put in there. And since you're using a volumetric flask, you dump both of those grams in there, and then you add water up to 250 milliliters. And there's your buffer. Does that make sense? If you were using and you could actually, it wasn't as good as this one with this, but if you were using the ammonium hydroxide one, the NH3 and the NH4Cl, the ammonium chloride, then you would have to use M1V1 instead of using this. you would say my final volume will be 250 milliliters. I know the concentration of that because it's written on the bottle. That would be your initial molarity. Your final molarity would be this, 0.01. And then you would need to find how big the cap is, or what, if you remember how we talked about that last year. But you would find out how much you want to put in of that into the solution. Right? Everything for you guys is already pre-measured, like the cap for, liquid detergent for the laundry, or now it's even just a pod. But most of the time, chemists use M1 V1 equals M2 V2 to find V1 because they want to know how much of that stock solution to use. Yeah. Questions at home? So tomorrow we'll give you a pH to work with, and then we'll put you in groups, and then you'll figure out basically how to make that buffer. Thursday, you'll make the buffer. Friday, we'll titrate it to break the buffer. Yeah. All right, that's all I got for today. Diego, are you coming or not? Because you really do need to tell them that you're not, because I don't want you to be like in the position where some